Everyone, welcome back. Today we are going to be working on section 10.2, which is another method of accounting. So on 10.1, the previous section, we learned about systematic listing, and we just talked about listing items with one part. We talked about product tables when there's a two task. And then if it's a multitask, we also looked at tree diagrams, one example of a tree diagram and a polygon, which was the last example that we saw. Now, in section 10.2, we're going to be talking about the fundamental counting principles. So using fundamental counting principles, what are the objectives of this section? We are going to be stating the meaning of a uniform in counting. So there's a uniform way of counting, the fundamental counting principle. We're going to be using the counting principle formula to actually solve problems. We are going to look at factorials and different ways on how to calculate a factorial. We're also going to be using our calculator. And then we're going to look at three kinds of orders that are important to counting process. So there's a specific order we need to follow. And then we're going to be using factorials to look at the number of different arrangements, including distinguishable arrangements. So there's a difference between arrangements, between distinguishable arrangements, and a number of objects. So let's go ahead and get started on the definition of a uniformly criterion. So when you're given a multi-part task, it's said to satisfy the uniform criteria. So what is that uniformity criteria? So if the number of choices of a particular part is the same, no matter how many choices are selected from previous parts. So that means that order will not matter. So no, it doesn't matter the choice from the previous part. So it's a uniform criteria. And what does the fundamental counting principle says? So when a task consists of k different parts, it satisfies the uniformity criteria. If the first part can be done in n1 ways, and then the second part in n2 ways, and so on until the kth part. So if there's four ways, would be 4 times 3 times 2 times 1. So it's a product principle. So the counting or the fundamental counting principle is treated as a product principle because you're multiplying the parts. So n1 times n2 times n3 times n4 times nk. So the task is given by the product of the task. So for example, if we're looking at the first example, it's saying counting two-digit numbers. How many two-digit numbers can be set from the set 0, 1, 2, 3, 4, 5? So we have 1, 2, 3, 4, 5, 6 choices, and there's two digits. So that means that we are going to look at the number of ways, how many two-digit numbers can be made. But there's a key word. Numbers cannot start with 0. So we're going to remove the option 0. So it's 1, 2, 3, 4, and 5. So it's 1, 2, 3, 4, 5 ways. So the first digit, there's 5 ways you can select the first digit, and the second digit is 6 because you're going to put back the 0. So for the first digit, you can't use 0 for the second one. So you have 5 options for the first. So 5 options and then 6 options for the second digit because 0 is allowed here. So if 0 is allowed, you have 0, 1, 2, 3, 4, 5. That's 6 options. So 5 options times 6 options gives you your total options. So the total number of options is the product. It's going to be the product of the first option, or the first, times the second digit. So 5 options for the first, 6 options for the second means a total of 30. Now, when you're building a two-digit numbers with restrictions, so notice that we had a restriction on the first part. On the first part, we had how many digits that do not contain any repeated made from the set. So we would have to remove some options. So then if we look at, let's say, at a product table, or the rules, let's say for the first one, it's saying how many two-digit numbers that do not contain repeated digits. So a two-digit number would be the first one would be 5. The second one would be 6 options, right? So 0, 1, 2, 3, 4, and 5. So you would have 30 minus the options that contain repeated digits. So 11, you would remove the option 11, um, 22, 33, 44, and then 55 because they contain the same digit. So then you're removing 1, 2, 3, 4, 5 options. So 33, sorry, 30. So this is 30 choices. So it'd be 30 minus 5, which is the repeats. That gives you a total of 25 options. So 25 would be um, the solution. So because you have 5 repeated digits, so 11, 22, 33, 44, and 55 are repeated digits. So from the 30, you have to remove the repeats, which will give you your total sample space. Now, does order matter? The following 3 kinds of order matters in accounting. So when you have order in which the components of a task outcome appear, so looking at example 4 and 5, we're going to look at examples 4 and 5. When selecting 2 officers, A and B and A, 2 distinct classes or 2 distinct cases, order matters. When selecting members of a committee, order does not matter. So 2 members of a committee, A, B, and BA are the same versus if there's 2 distinct cases, A, B, and BA are different. So if they're different, then that means that we're going to have a different case. So A and B and B and A can be the same if you're looking at a committee. But if they're not in a committee, then A and B and BA are different. We're also going to look at a second part, order of organizing a list. So what happens if we wish to organize a list in a different way? So we're going to look at an example 9 from the previous section, which determines the number of triangles. So remember when we saw that example where we had this triangle and then within those triangles, there were different types. So then we can rearrange it in a way that we can do it in alphabetical order or by the regions. So those are the different types of ways we can arrange our tasks. That way we're able to count them properly. And then the third one, order of considering tasks. So again, from the previous example, where selecting a secretary and then the president, or first the president and then the secretary, it actually satisfies the uniformity criterion. So that means we are able to use the product principle or the fundamental counting principle. So it would be the number of tasks. So for the first task was 4 so 4 ways of selecting a president. And then we had 4 ways. So for a president and a secretary, we had 4 ways and 4 ways, but then we had to remove both positions. So when we were looking at removing the both positions, we removed M, A, T, T, H, A, and then A, A, right? So we had to remove those 4 options. So we did 4 times 4. 4 times 4 minus 4, that would be 12 ways. So that satisfied the fundamental counting principle, which is 4 options for a task, 4 options for another task, but then remove when they're both at the same case. So let's look at example 5. So let's start performing some examples. Alrighty, so let's go ahead and look at a counting license plate. How many ways can you select 2 letters followed by 3 digits? So 1, 2 letters, 2 letters. So This is the alphabet. How many alphabet? Alphabet. And then followed by 1, 2, 3 digits. So digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 10 ways. So I have 10 ways, 10 ways, and 10 ways. It doesn't mention, so note repetition is allowed. It doesn't say anything about not allowing repeats. So that means all of my 10 options, all of my 10 digits are allowed. And the alphabet, same thing with the alphabet. So there's 26 letters on the alphabet and 26 letters. So that means I'm going to use the fundamental counting principle. That means, okay, well, I have 26 options for the first task, 26 options for my second task, and then 10, and then 10, and then 10. So that means I'm going to take the product of 26 and 26, or 26 squared times 10 to the third power. And here, this is where I'm going to use my calculator. So if you can go ahead and I'm gonna show up my calculator. It's a nice resource to have. It's called Calculate 84. It's a free device. So let me go ahead and share that screen. So this is my calculator. It's a free calculator. It's called Calculate 84. So if you have a MacBook or an iPad or an iPhone. Um, this calculator device, it's free. It's actually a graphing calculator, so it's a very nice device to have. So I'm going to do 26, and then I'm going to take that to the square. I'm going to take that product and multiply it by 10 raised to the third. And then I'm going to get my solution, which is 676,000 possibilities. And that will be my solution, which is using the counting principle. So now let's talk about the definition of a factorial. What is a factorial? So a factorial, for any counting number n, the product of all counting numbers n down. So that means you're decreasing in size. It's called n factorial. So it's n factorial. It's the same as n times n minus 1 times n minus 2 times dot 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 dot. So all the way up to n minus whatever number it means. So we have n minus 1, n minus 2. That is called the factorial formula. So let me give you a definition. If it's a 3 factorial, that means 3 times 2 times 1. So that is 6, because 3 times 2 is 6 times 1 is 6. 0 factorial by definition is 1. So 1 factorial is 1, just 1. 0 factorial is also 1. 0 factorial is not 0, okay? So just be aware of that. What if I want to evaluate 4 factorial? So let's look at 4 factorial is the same as 4 times 3 times 2 times 1. 4 times 3 is 12, times 2 is 24, times 1 is 24. So 4 factorial is 24. You can also use your calculator to identify factorials and made it easier. So if I'm in my calculator, I can go into 4, and then I'm going to go to math, and then I'm going to go to prob, and then select that factorial. So that's 24. 4 minus 1 factorial, I'm going to put parentheses, 4 minus 1, close it, math, prob, 4. There's my answer, 6. And lastly, 5 factorial over 3 factorial. Well, I'm going to do 5 and then factorial, math, prob. So 5 factorial is 120 divided by 3 factorial. So 3 factorial is 6. So 120 over 6, that's 20. 120 over 6, we get 20. So therefore, we were able to solve all of my examples, A, B, and C. So I have 4 factorial, 4 minus 1 factorial, and 5 factorial over 3 factorial. Now let's talk about the arrangements of objects. So when we're finding the total number of ways to arrange the arrangement of objects, we're going to look at this factorial principle. So this factorial principle is looking at the different ways we can arrange the number of different objects or distinct objects. So the total number of different ways to arrange n objects is n factorial. So if it says a range of n items, then that means you're going to take the factorial of that many items. Let's look at this different one. How many different ways you can line up 6 different books? So there's 6 different arrangements. So the 6 is the factorial, is the number of ways, is the number of arrangement. That would be the number n. So it's going to be 6 factorial, or 6 times 5 times 4 times 3 times 2 times 1. And then here we have 30, and then here we have 24, because 4 factorial is 24. We can multiply 30 times 24, or we can use our calculator. But when we do 30 times 24, we get 720. So our solution are 720 different arrangements. Now, there's a difference between arrangements and distinguishable arrangements. When you want to find the number of distinguishable arrangements, we're going to look at the total number of arrangements divided by the repeats. And the repeats will also have factorials. So we have distinguishable arrangements with divided by the repeats. So let's look at an example that will satisfy something that looks like a distinguishable arrangement. We wish to count the distinguishable arrangements of the word initially. So the first thing you do is you count the word initially. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's a total of 9 digits, or 9 letters. So it's going to be 9 factorial over the repeats. So who do I have repeats? I, 1, 2, 3, 3 I's. So it's going to be 3 factorial with the I's. So 3 I's. Another N, L would be twice. And then 2 L's. So 2 factorial. A doesn't repeat, Y doesn't repeat, and N doesn't repeat. So the only repeats are on the bottom. So then I have 9 factorial, where I'm going to use my calculator here. 9 factorial is 362,880 divided by, well, 3 factorial is 6 times 2, that'd be 12. So now using my calculator, 362,880 divides by 12, I get 30,240. So 30,240 are the number of distinguishable arrangement. Not arrangement, but distinguishable. Distinguishable arrangements. And that ends section 10.2. Thank you guys. I'll see you guys next time. Bye-bye.